How you doing? I'm Mr. Rose, and today we're going to talk about, sorry, let me scroll up here a little bit. There we go. Today we're going to talk about the J.J. Thompson model of the atom, question 22.54 in your textbook. And the textbook is Young and Freeman, the 13th edition. So I want you to take a minute. There's a lot of stuff in this question, but it's a really cool question. So take a minute. We're going to go back and forth from A to B to C, so I'll show this question a few times. But obviously, we're going to start with A, and we're talking about, again, the J.J. Thompson of the model. And that J.J. Thompson of the model was that the model was this sphere of a positive charge, kind of like a goo. And there are negative things that are distributed through, and it's the chocolate chip cookie model, the plum pudding model, whatever you want to consider it. Well, for us, for part A, we want to explain why the equilibrium position of the electron must be at the center of the nucleus for an atom consisting of one electron. Now, this may go in a little bit of an opposite direction of what J.J. Thompson was saying, is that the negative is going to be somewhere displaced in that positive charge. So let's just discuss Gauss's law. We can actually talk about this without even writing anything down. So to discuss Gauss's law, we know that the flux through any Gaussian surface is equal to 1 over epsilon, right? We said let's consider the density of the field lines, and they're going to be per unit area, and everyone is going to agree to draw the same number of lines in this factor of 1 over epsilon naught, where epsilon naught is the permittivity of free space. Well, no matter where I would put that negative in my atom, the flux could be the same, but the electric field is a factor of distance. So if my, well, first of all, if I encompass the entire atom, or if I drew my Gaussian surface around that entire atom, I would know that the electric field has to be 0 because the positive atom and the negative electron are going to cancel out, so my net electric field around that whole thing is going to be 0. All right, so it's an equilibrium position. I'm sorry, how do I know that it's an equilibrium position and the equilibrium position at the center? Well, if the atom or the electron is moving around or is in a different place other than the center and the nucleus, right, what would that impose to us? That would impose to us that there may be an electric field on one side of the atom versus the other. And we know that can't be happening, right? The electron, the atom, had to be stable, and if there's no net electric field, just like drawing again that Gaussian surface around the entire thing, we have to assume that the equilibrium position of that electron has to be at the center of my atom. So that negative, bam, right in the nucleus, where the positive then is going to be all around it in a nice equilibrium stable position. Now we're going to look at part B. Part B, take a minute to read. And now that you've read, let's get to it. All right, so there's a lot to this question as well. This is talking about if I displace my electron, it's going to oscillate back and forth, possibly like simple harmonic motion. So we're going to need to see if it actually models that. All right, so for part B here, we're trying to figure out if the electron is going to oscillate in the same manner as a simple harmonic oscillator. Now, according to the reading, it says that the positive charge offers little to no resistance. So how are we going to be able to check this to know if we have this? Well, I'm going to use Gauss's law, but really Gauss's law is going to show us things that we already know, right? So remember that Gauss's law, enclosed integral of E dot dA is equal to Q enclosed over epsilon 0, right? So now when I take this, this is going to be just a quick summary and review. We know the enclosed interval of E dot dA. We know those are both vectors. We know that's going to be E times A. We've got a sphere. We're talking about surface area. So I know this is the electric field times, forget about my dot product, times 4 pi r squared. That is my EA. Now Q enclosed is going to be the charge E because that's what they told us in the problem. And that's going to be over epsilon 0. All right, so now that means I can derive, and we've done this before, the electric field for a point charge, and that's essentially what we have, but for a sphere, is going to be E divided by 4 pi r squared epsilon naught. All right, so that's nothing we haven't seen before. That is just a straight derivation of Gauss's law. Now, how is this going to be helpful for us? Well, we know that we've got this charge density, right? And remember, a charge density by definition is my charge per unit volume, where the volume of the sphere is 4/3 pi r cubed. So now I can substitute this in for here, and I'm eventually going to take this. I want to solve for E because I can put my charge in for my electric field. So let's just try and do that here. So here's my electric field. Here's my charge for E. So I should be able to now put these things together. So I should get something like, had to do some rearranging there, sorry, so I can see everything on my screen. So as I said, we've got my electric field, we've got my charge E. We're going to substitute these two things together. Now remember, we're trying to see if there's an oscillator back and forth, a simple harmonic oscillator based on this displacing of my electron. This also kind of talks about part A, why it needs to be stable in the center, stable around that equilibrium center. So here's my electric field, here's my E. We're going to substitute in. We're going to get something like E equals, that looks like it's right, over 1. So we should get an electric field equal to a rho times an r, like density times r, over 3 epsilon 0. 3 epsilon 0. So that is my electric field. So what is that helping us to do? Well, let's remember, move this aside, let's remember that our simple definition of force, what is the electric force? Electric force is just negative Q times E. We've done that before, where my negative Q is E in this case, right? Because they told us that in the problem. So I say F is equal to negative E times my electric field. And I can make a direct substitution for E. I'm sorry, not for E, for my electric field, what we just solved, right? I just solved for that electric field. So I can say the force, negative charge, times rho r over 3 times the permittivity, epsilon naught. And this is what I was going for. What am I going for that? What was simple harmonic motion? Simple harmonic motion told us that the force was directly proportional to a distance that goes back and forth. And the negative implies that it's a restoring force. That's what we got going on here, right? Simple harmonic motion, if you recall, F equals negative kx, was directly, this stuff, directly proportional to some distance. And this is a constant. Look, all these things are constant. So this is exactly what it's telling us. So we do see that our electron does exhibit some simple harmonic motion. All right, so I cut back to our problem. Now that I showed that it's going to be in some simple harmonic motion kind of form, I want to calculate its frequency. So that's what we're kind of looking to do. Okay, so as I said, my constant and my constant are going to kind of match up. So I'm just going to say that. I'm going to say let K equal this constant, rho times pardon me. R is not my constant. E is my constant. So I'm going to let my constant be rho E over 3 epsilon naught. And it's going to be a factor of the radius. I don't know, so I definitely misspoke before. Hopefully you picked up on that. But I'm going to let that be my constant if I'm in this form, right? Where my radius is my radius or my distance x. So recall also the frequency of oscillation is going to be 1 over 2 pi times the square root of k over m. That should be something we know. This is going to be a direct substitution that's going to get ugly, so it's going to take me a second. The frequency is equal. So that looks like I have a frequency of 1 over 2 pi times the square root of rho, which is the density of the atom, times the charge of the atom, divided by 3 times m, times my permittivity of free space. Whew! Now, that's sort of helpful, but I think I can simplify things more. In other words, rho was something we kind of derived. Rho was the density of the atom. Well, where can I find that density of the atom? I know rho was equal to 3/4 times the charge times pi times r cubed. So I can now get this general density out to make, again, another substitution. Need my paper over there. So here I have my substitution in for my density times my E divided by 3 times mass times epsilon 0. I can simplify this out. So I have a frequency equal to my frequency 1 over 2 pi times my charge squared over a whole bunch of constants of 4 pi m epsilon naught. Now there's my factor of r. There's my radius r cubed. So the frequency of this sucker of oscillation that does fall into the form of a simple harmonic motion, 1 over 2 pi times the square root of the charge of my atom squared divided by how much it's a whole bunch of constants times r cubed. So that factor of displacement. Now, part C is really kind of cool, and this is, again, kind of to show you that even as wrong as Thompson's model was, it wasn't out of the question. Well, what the heck does that mean? What are we looking for number 3? Well, again, part C, rather, it's talking about light emitted, excited electrons. We should know this from chemistry. But from that, we can actually try and figure out, where does it say, what is the radius of the Thompson model of the atom for it to produce this red light frequency. So this is almost, well, it is just a plug and chug, but it really is an application of, holy cow, think of the amazing stuff that was going on at this time. Let's get to the piece of paper. All right, so to try and find the radius based on the frequency, let me just copy my frequency down from before. Frequency. That looks better. Get that on camera now. There we go. So my frequency is 1 over 2 pi times the square root of the charge squared over 4 pi times mass times epsilon naught times r cubed. Now, they told us in the problem a couple things. I've got the problem just still up on my screen. We know that the charge E is 1.6 times 10 to the negative 19 coulombs. We know the mass of an electron is 9.11 times 10 to the negative 31 kilograms. We know epsilon naught, permittivity of free space, to be 8.85 times 10 to the negative 12 coulombs squared per Newton meter squared. And they gave us a frequency of 4.57. 4.57 times 10 to the 14th hertz. Now again, although this is just a straight plug and chug question, it is super interesting to try and think about what we get out of this. So a quick rearrange. R is equal to, I gotta Make that to the 1/3. Okay, so here is my radius. Plugging all that in, r is equal to 1.6 times. If I put all of that into my handy dandy TI 89, you should get something like a radius of 3.13 times 10 to the negative 10th meters. Now, why that seems trivial, that actually shows you that the radius given by losing energy with the frequency of somewhere in the red light spectrum gives us something that is a relative atom size. Meaning, even though the physics that they imparted was incorrect, we knew the shape of the atom, we knew the charge of the atom, we knew the size, the radius of the atom, and though this plum pudding model indicated that there had to be, his plum pudding model or chocolate chip cookie model indicated that he thought there were negatives distributed throughout. If we're talking about one electron, which is, the Bohr model, that was what came next. And the Bohr model was a solid positive proton in the nucleus where the electron is orbiting around, but the electron is still orbiting around in a stable equilibrium. Right? It was in those electron shells. Even with the electron cloud model, we still have the shape in the area, I shouldn't say shape, where those electrons exist. All the way back in the 1910s when J.J. Thompson figured all of this out. Very long problem, very interesting problem, I believe. That's all I have for you today. Please feel free to like, comment, or subscribe, and please feel free to see me next time and do the next problem. Also part of J.J. Thompson.